So, as we said before, the shift cipher is just a special case of substitution cipher, where we can use only 26 out of 26 factorial possible permutations. Another special case of the substitution cipher is the affine cipher, where the encryption function has the form A multiplied by plaintext letter plus B modulo 26. So, as we noticed from this encryption function, the key consists of two parts, A and B, and note that if we have A equal 1, then we have just an ordinary shift cipher. In affine ciphers, our plaintext and ciphertext are also letters of English alphabet, so we can encode them from 0 up to 25. Then we can define our key as a pair of numbers which are also in the set of integers modulo 26. But we have one more condition. We need the greatest common divisor of this A part of the key and modulus, which is 26 in our case, to be equal 1. After we define our key in this form, we can define our encryption algorithm, which we have seen in the previous slide, and we can define our decryption algorithm. So here we have one more term, a to power minus 1, which is called multiplicative inverse. But before I explain what multiplicative inverse means, let's check if the message, encrypted message, is decrypted using the same key. This will give us the same plaintext. Our plaintext is equal to decryption of ciphertext with the same key. If we substitute this C by the decryption algorithm, this is our decryption algorithm, we substitute this C by the value of ciphertext, we will obtain this type of expression. So B's are cancelled. We are left with a to power minus 1 multiplied by a and multiplied by plaintext. So this term, multiplicative inverse, should be a unique number. When multiplied by a, it should give us 1. Therefore, this element a to power minus 1 is called a multiplicative inverse of the element a. So, why we are left with the plaintext only? Because we have this part in this expression as well. When we multiply a to power minus 1 by a, yields the multiplicative identity, which is equal to 1. So, since our alphabet consists of 26 letters only, this mod operation will give us the P itself. So the decryption is correct since the receiver can decrypt and read the message. So from the previous slide we see that decryption in a fine cipher is possible if and only if the affine function is injective. Let's define what the term injective means. For any number which belongs to the set of integers modulo 26, which we denoted by z with subscript 26, we need the congruence, that is the equation of this type, to have a unique solution. If this congruence has a unique solution, then we call this congruence to be injective. Let's define what is a congruence. An equation of this type is called a congruence, and we need to solve this equation with respect to this x. But the point is that the congruence of this type has a unique solution for y if and only if the greatest common divisor of a and this modulus, in our case this is 26, is equal to 1. In other cases, this equation will not have a unique solution. So, for example, in the case if we choose the a part of our key is 4, then our encryption function will look like this, that is p multiplied by plaintext plus 7 mod 26. But this is not a valid encryption function because we will not be able to decrypt a message encrypted with this pair of keys. Let's see why this function is not a valid function. Before, we have defined our encryption algorithm and decryption algorithm. To show how the decryption algorithm works, we need to understand some topics from modular arithmetics. First, we should recall what a set of integers modulo m means. A set of integers modulo m, which is denoted by zm with subscript m, is a set of residues when divided by m. So it consists of numbers from 0 to m minus 1. These numbers are called elements of this set, and for some elements of this set we can define a multiplicative inverse of an element. How we are going to define this multiplicative inverse? This multiplicative inverse is also an element of the same set, and this multiplicative inverse should give us the multiplicative identity, which is 1 when multiplied by the number itself. But the point is that an element can have a multiplicative inverse if and only if this element has a greatest common divisor, which is equal to 1, with the modulus with respect to which we are doing our calculations. In this case, these numbers a and m are called relatively prime numbers. If we are back to our alphabet, which consists of 26 letters, then our set of integers which can have a multiplicative inverse, that is, set of integers for which greatest common divisor of number and the modulus, that is 26, is equal to 1, is these numbers. So we have 12 elements which are coprime to m. We can calculate a multiplicative inverse for each element. So when 1 multiplied by 1 is equal to 1 modulo 26. 5 multiplied by 21 will give us 105, and if we divide it by 26 we will have 1 as a remainder. So for 5, 21 is a multiplicative inverse, and so on. As we can see, the inverse of an element also belongs to the set of integers modulo 26. Now let's see how a fine cipher works. Let the a part of our key to be equal to 9 and b part to be equal to 0. So we are working with the encryption function defined as c, which is equal to 9 multiplied by plaintext letter plus h. And suppose that we are encrypting the plaintext h. The position of h letter at the alphabet is 7. With this particular key, which is equal to 9 and 2, we can compute the ciphertext. Our ciphertext becomes equal to 65, and if we divide it by 26, we are left with a remainder 13. 13 is our desired ciphertext, and 13 is a letter n. So using the same logic, we can encrypt every single letter of the word affine to obtain this ciphertext. Let's decrypt it. For decryption, we will start with encryption algorithm. The natural way to find the plain text from this equation is to, without taking the modulo part into account, we would calculate p as a c minus 2 divided by 9. Since the greatest common divisor of 9 and 26 is equal to 1, we can find the multiplicative inverse for 9 modulo 26. We can calculate it, and we will see how to calculate the multiplicative inverse later. So we can see that if we multiply 9 by 3, the remainder after division by 26 is equal to 1. So 3 is the multiplicative inverse of 9 modulo 26. We can decrypt our plain text by using this key. Let us consider another example. This time we choose A to be equal 13 and B to be equal 4. So we are working with the key 13 and 4. Our ciphertext is going to be equal to 13 multiplied by plaintext plus 4 modulo 26. If we encrypt the plaintext input, we obtain the word ERRER. But the point is that if we encrypt plaintext alter with the same key of 13 and 4, we are going to obtain the same ciphertext. This is because the greatest common divisor of 13 and 26 is equal to 13. There is no multiplicative inverse for 13 modulo 26, so encryption is not possible since mapping is not one-to-one. And this is why we have two different messages which are encrypted to the same ciphertext, even though we encrypted both messages using the same key. So, for a fine cipher to be one-to-one, that is, to be able to decrypt the message encrypted using a fine cipher, we need to choose the key which consists of parts A and B, such that the greatest common divisor of A part of the key and M, that is modulus. In our case, the modulus means the number of letters in the alphabet, to be equal to 1. Now, let's consider the cryptanalysis of fine ciphers. Fine ciphers, as well as shift ciphers, are very unreliable. First, we will consider ciphertext only attack. In fine ciphers, two parts of the key A and B can be selected only from the set of numbers from 0 to 25, since for English language the number of possible keys is only 26. However, unlike shift ciphers, we have a condition for choosing the first part of the key. That is, we can choose an element A only if the greatest common divisor of A and 26 is equal to 1. That is, for an alphabet with 26 letters, the choice of elements for as the first part of key is restricted to 12 letters only. Our key space is 26 choices for B multiplied by 12 choices for A makes 312 possible combinations of A and B. In ciphertext only attack, an adversary has only the ciphertext. Since the key space is small enough, we can use ciphertext only attack as we need to try less than 300 possible keys. We can use ciphertext only attack as we need only 312 possible keys. Note that if we take A part of the key to be equal 1, we are dealing with shift cipher with even smaller key space. And if in addition we have B to be equal to 0, then we are going to end up with plain text itself, as it gives 0 shifts. So, if we exclude these trivial cases, the number of possible keys reduces. So, the best strategy for cryptanalysis of fine ciphers is an exhaustive search, since we are left with less than 300 possible keys. And if the message is long enough, we are going to have only one meaningful message that would be our desired plain text. Another method that we can use for cryptanalysis is to use frequency count. However, to apply this method, we need much longer text. So if we know two letters of the plain text and its corresponding encryption, we can break this cipher with less effort. Suppose that somehow we obtained a pair of plain text and ciphertext. That is, we know that our plain text starts with word if. This word is encrypted as PQ. We know that I is the ninth letter in the alphabet, and this is encoded as 8, and F is encoded as 5. Encoding for P and Q is 15 and 16 respectively. So if we put these numbers to our encryption equation, we have the system of equations, and subtracting the second equation from the first one, we can calculate the value of a part of key, which is 17. If we substitute this a key to the first equation, we will easily obtain the b part of our key. And if we have the possibility to choose plain text, then the easiest way is to choose the combination of letters A and B, since our equation then becomes very easy to solve. And if we are working with ciphertext, then we are going to choose A, B letters from the ciphertext again, and solving this equation, we can easily obtain the encryption key. Prior to this, we have mentioned frequency analysis several times. What is the point of frequency cryptanalysis? This type of analysis is a very powerful tool to cryptanalyze monoalphabetic ciphers. So the point is that any human language has different frequencies for different letters in the alphabet. This is called the probability distribution of letters in the language. The basic cryptanalytic attack against monoalphabetic substitution cryptosystems begins with the frequency count. That is, we count the number of each letter in the ciphertext. For many languages, the official distribution of letters has been already calculated, so we can prepare this attack on a cipher just by comparing the distribution of letters in the ciphertext with some official distribution of letters in the plaintext languages. The letter with the highest frequency in the ciphertext is likely to be substitute for the letter with highest frequency in plaintext language. Therefore, this method of cryptanalysis is called the frequency analysis. For the accuracy of frequency cryptanalysis, we need the length of ciphertext to be as large as possible. So in this slide we can see the frequency counts for English and other languages. Let's try to cryptanalyze a ciphertext encrypted using a fine cryptosystem using frequency analysis. So let's assume that English plaintext is divided into blocks of 5 letters. Note that space and punctuation is ignored. So we will try to find the corresponding plaintext. How we can do it? First of all, we are going to count the occurrence of each letter in the ciphertext and sort them in decreasing order. We obtain this frequency distribution, and here we have the official distribution of letters in English language. Now we can just compare these letters. We first assume that this letter E is encrypted as X and the letter T is encrypted as U, since these are the most frequent letters in our ciphertext. Our equation becomes like this. So by subtracting the second equation from the first one and doing the simple math, we can deduce that a is equal to 5 and b is 3. With this key, we can make our translation table. So if we use this key, then a is encrypted to p, b is encrypted to k, and so on. Now, using the provided description table, we are trying to decrypt our message, but we can see that our plain text starts with K, G, W, T, G, and so on, and this text does not make any sense, so our guess was incorrect. We can try some other combination of letters. This time, let's assume that the letter E is encrypted as X, but we take the pair A and H, and our equation, the system of equations, can be written in this form. We have immediate solution for B part of equation. For A, we have two choices, either 4 or 17, but greatest common divisor of 4 and 26 is not equal to 1. Therefore, we choose the A part of key 17, and with this key of 17 and 7, we have this translation table, that is A is encrypted as V, B as S, and so on. Using this translation table, we can decrypt our ciphertext, and this time we obtain some meaningful text. We can say the main point of monoalphabetic ciphers is that once a key is chosen, each alphabetic character of a plain text is mapped onto a unique alphabetic character of the ciphertext. Therefore, cryptanalysis of this kind of ciphers is very easy. People come to decision to use polyalphabetic ciphers, which we are going to study at the next lesson. So this is all for monoalphabetic ciphers. Thank you for your attention. Bye bye.